I'll just let people settle down a bit. Okay. As you'll probably have noticed, I'm not Eric. Apologize for that. I also want to apologize for the fact that unlike most of the other talks you've heard at this summer school, I'm going to be talking about stuff that's really old. In fact, this is probably older than a lot of the people in the audience. But I think it's interesting because, well, naturally I would think it's interesting because this is the aspect of active matter that got me into this field. In fact, it got me into the field before the phrase active matter had actually been coined. And it's still, to me, one of the most striking examples of how different an active matter system can be from an equilibrium system. And so that's what I want to talk about. So I'm going to be talking about a continuum theory of flocking. The original idea that physicists might have something to do with the phenomenon I'm going to call flocking is, of course, due to Thomas Vicsek. And all the work I'm going to talk about, and a lot of the words you'll see in the notes that were distributed, were co-written with Yuhai Tu of IBM Research. I'll show you a few simulations that were done by Marcus Ulm, who was an exchange student at the University of Oregon some years back. And of course, everybody who works on this field is inspired by Alfred Hitchcock. Okay, so I'm using flocking in a rather technical sense, but in a way I'm using it in a very conventional English sense. By a flock, I just mean a bunch of critters that are all moving in the same direction. Okay? And the critters aren't necessarily actually living things. They could be self-propelled little molecular motors. They could be synthetic robots, whatever. Any large collection of things that are moving in the same direction is what I mean by a flock. And something I want to emphasize here, because it's going to play a big role in these lectures, is the role of dimensionality. Okay? So flocking is something that can happen. The usual flock you think about as a flock of birds, and that, of course, is moving in 3 dimensions. It's moving in the 3-dimensional space of the air, but it can also happen in 2 dimensions. And here's an example of a rather large 2-dimensional flock. This is a herd of several 100,000 wildebeest, and it's a still picture. I'm sorry, I'm not good enough at the technology to show you a movie of this, but trust me, all of these wildebeest are moving in the same direction. They're all moving, I believe, to the right. And there's a lot of interesting things going on here. There's this weirdly shaped front, and so on and so on. But to me and to Thomas Vicsek, the thing that's really striking about this is that this wildebeest over here, shown in yellow, is moving in the same direction as, say, some randomly chosen wildebeest over here, but this wildebeest certainly cannot see that wildebeest. Okay? Somehow, the information about which direction this wildebeest is moving is being transported through this immense space, essentially by word of mouth from one wildebeest to the next, until it gets essentially uncorrupted to the wildebeest up there. And what got me into this field was Thomas Vicsek talked about this phenomenon and pointed out that as a condensed matter physicist / statistical physicist, I should know that this is impossible. And I'm going to tell you about that in a few minutes. This apparently violates something called the Mermin-Wagner theorem. God, I hate these things. And that's pretty scary because we don't have very many theorems in physics. There aren't too many things that we're so sure of that we call them theorems, but one of them is the Mermin-Wagner theorem, and here's an example that seems to violate it. And so what got me into this was trying to understand how this thing could happen. Okay, so it can also happen in 3 dimensions. It's a bit depressing that both of these pictures come from Africa. Apparently, the only place where you can see big enough, large enough collections of animals that you don't need a microscope to see them anymore in the world is in Africa. So this is a flock of flamingos. This is actually a 3-dimensional flock. It's almost as extended vertically as it is horizontally. It also contains about 300,000 creatures. And again, a flamingo over here can't see a flamingo over here, but they're all going in the same direction. This turns out to be not too surprising. This is something, the sort of phenomenon could happen even in an equilibrium system, but the 2-dimensional phenomenon is very bizarre and should be impossible, apparently, one would think. So here's another example. Now the visual quality here is really going downhill. This is just a hand-drawn cartoon, but trust me, this is what really happens. Vicsek got interested in this problem because some biologists were studying pattern formation in the growth of bacteria colonies. And they showed him some films of this, and he, like all good contrarians, focused on the pictures that they thought were really boring. These were pictures in which the bacteria colony was just growing in a circle. And Vicsek noticed that if you looked inside that bacteria colony, the individual bacteria were not moving around at random. They weren't moving like the air molecules in this room, which are flying in every different direction with equal probability. They would all be circulating counterclockwise, at least in the first one he looked at. And then he noticed that if you looked at other circular colonies, with a 50% probability, they'd be circulating either counterclockwise or clockwise. Okay, so it wasn't that the bacteria were intrinsically left-handed or right-handed, and that's the reason they chose one direction to circulate or another. That seemed to be a spontaneously broken symmetry. Okay? And Vicsek had the idea that maybe the symmetry that's really being broken here is not a discrete left-right symmetry, but a continuous symmetry. That in other words, what was really happening here was that all these bacteria were trying to move in the same direction. Okay, so if there wasn't a boundary, if the colony didn't have a boundary outside of which conditions changed and repelled the bacteria, this whole group would just move in the same direction coherently. If that's true, this is bigger than either of the flocks that I showed you before, because these colonies can contain as many as 1 billion bacteria. Okay, so why am I puzzled by this? Well, I'm not anymore, but back in 1994, when I first heard this story, I was extremely puzzled by this. And Vicsek was aware that we should be puzzled and actually sort of rubbed our noses in it. He said, this, of course, as you know, violates the well-known Mermin-Wagner theorem. So let me tell you what the Mermin-Wagner theorem says, for those of you who haven't heard this before. The Mermin-Wagner theorem says that you cannot spontaneously break a continuous symmetry in a system with short-range interactions and noise in 2 dimensions. Okay, so in other words, how does this violate that? Well, presumably, the bacteria can't tell one direction from another. They presumably aren't carrying compasses. Now, there are species of bacteria that do carry compasses. They use them to tell which way is up and which way is down, not which way is north and which way is south. But these bacteria that are doing this don't. Okay? So they have no way of telling one direction from another except by looking at their local environment. The only thing there is in their local environment is other bacteria. So the only thing that can be leading to this kind of coherent motion is one bacteria trying to align with its neighbors, that bacteria aligning with its neighbors, and the information somehow propagating through an enormous flock. Okay? If you don't know the Mermin-Wagner theorem, you say, well, so what? So that's what happens. But the Mermin-Wagner theorem says that precisely that thing cannot happen in 2 dimensions. Or let me phrase this another way that will explain all these buzzwords up here. Okay. The underlying dynamics of these bacteria have a continuous symmetry. They don't have a preference for moving north, south, east, or west. All those directions are equivalent as far as the bacteria are concerned. Yet the state the bacteria go into clearly does not have rotation invariance. There's a special direction picked out, namely the direction they move in. So the underlying symmetry of rotation invariance, which is a continuous symmetry because you can rotate by any angle, is spontaneously broken in this system by the interaction between the bacteria. Okay? That's just another way of saying, what we just described. The Mermin-Wagner theorem, however, says that if you only have short-range interactions, and presumably there are only short-range interactions here, a bacteria on one side of this colony can't see a bacteria on the other side of the colony, firstly because they don't have eyes, and secondly because light wouldn't be able to travel that far anyway because there's too many bacteria in the way. Okay? So whatever's happening here is happening due to short-range interactions, and what you're developing is long-ranged order. Apparently this can happen no matter how large the flock is. Okay? The Mermin-Wagner theorem says that if you're in 2 dimensions and your system has any kind of noise, any kind of randomness, the Mermin-Wagner theorem was originally developed for thermal systems, and so the noise was just thermal fluctuations, temperature. Here, thermal fluctuations probably don't play a role, but the bacteria presumably make mistakes, right? I mean, if I told all of you to go out and walk in the same direction, you'd walk in approximately the same direction, but there'd be some variance, some fluctuation in that, okay? So the bacteria are making errors in following each other. That's analogous to the role of temperature in an equilibrium system. They only have short-range interactions, and yet they're spontaneously breaking a continuous symmetry in 2 dimensions. The Mermin-Wagner theorem says that should be impossible. So every time you see a 2-dimensional flock, every time you see a 2-dimensional system of creatures that are all moving in the same direction, that's doing something that, on the face of it, violates one of the few theorems we have in physics. Okay? Well, that's the sort of provocation that'll get me to do something. Okay? So what I tried to do was understand this. And what we realized what Juhai Tu and I realized fairly early was that, of course, the Mermin-Wagner theorem doesn't really apply here. And that's, of course, a great relief, because you don't want one of the few theorems you have to turn out to not be true. It's violated because this is a non-equilibrium system. How can you tell it's a non-equilibrium system? Well, it's living creatures. Does it have to be living creatures? Well, they have to be living in a sense. They have to be living in the sense that they have an energy source that can overcome friction. And I should emphasize here, I'm talking about what these days the buzzword for is dry active matter. And what that means in this context is that these creatures are moving over some substrate with which they experience friction. So it's like me walking across this floor, okay? If I suddenly died, you'd be able to tell because among other things I'd stop moving, right? You need to be alive to be able to move, right? And you need an energy source that you need to be able to convert that energy into motion against friction. Okay, so that's the situation I'm trying to imagine here. So these things are moving, so they're clearly non-equilibrium. So if you want to take the coward's way out, what you say at this point is there's no violation of the Mermin-Wagner theorem because the Mermin-Wagner theorem only applies in equilibrium. That's true as far as it goes, but it doesn't explain anything. You know, what is it about the non-equilibrium nature of this problem, and in particular, what is it about motion that makes it possible to get around, seemingly get around this theorem? Well, what we discovered was that this non-equilibrium aspect of the problem leads to something called a breakdown of linearized hydrodynamics. That's a bunch of buzzwords that I'll defer explaining for later. But suffice it to say, it's a very bizarre phenomenon that until we studied this was considered fairly esoteric. Turns out to be essential for the existence of any two-dimensional flock, which is quite surprising. If you just do a linearized theory of this, you predict that the Mermin-Wagner theorem would hold for flocks and that you would not be able to get a two-dimensional flock. So you need to go to nonlinear order. And this nonlinear effect stabilizes the long-range order. That's the story I want to give you in these two lectures. Okay? So that's the idea. Here's the outline of what I'm going to say. Today, I'm probably not going to... Well, all right. I'll talk a bit about the microscopic model just to give you... I don't think most of the details of the microscopic model actually matter. I'm going to talk about the model due to Vicsek. It's a little computer simulation that he cooked up to simulate the motion of these bacteria. I'm going to give you all the details of this model, but the only important things about this model, the only things I think that really matter are that the underlying dynamics have rotation invariance, so the creatures only pick a direction to go by following their neighbors. They don't have any other reference. And the interactions are local. Yeah, there's a question back there. Good question. Yeah. So the claim is that the correlation length in these systems is infinite. That you could make this flock arbitrarily large and you would still see bacteria on one side of the colony moving the same, all the bacteria in the colony moving in essentially the same direction. So that's the question. Is it possible to have a state like that in an active system? We know that in an equilibrium system, it is not. Okay? In an equilibrium system, there'll always be some finite correlation length beyond which the correlations well, hold that question for a few minutes and I'll talk about the equilibrium analog and you'll see what I'm talking about. But yes, the assumption here is, well, the claim is that you can get an infinite correlation length in a system like this, even in 2 dimensions, and the question is why. Yeah? Ask me that question in 10 minutes. I'm going to discuss that. Yeah. If you haven't seen this before, the fact that the statement only applies in 2 dimensions may seem deeply mysterious. It actually applies in 1 dimension too, but 1 dimension is special because there's only one direction you can go, right? But I'll explain all, okay? All right, so I'm going to talk about this Vicsek model, but I want to emphasize that even though I'm going to describe it in a fair amount of detail, the only important things are rotation invariance and locality. Then I'll give you a derivation of the Mermin-Wagner theorem and tell you why it is that 2 dimensions is special and why it is that we expect not to be able to break a continuous symmetry in 2 dimensions. And that, of course, raises the horrible question, are birds smarter than nerds? Do they know something that we don't know? Then I'm going to describe how we actually understood this. And the way we understood this was to formulate a continuum model, which I always used to just call the continuum model, but finally I broke down and started calling it what other people call it, which is the Toner 2 model, just to be clear. Really not trying to brag, but it's just, this is the Toner 2 model, okay? And the great thing to me about this model is people have, since Yu-Hai and I wrote this model down in 1994, many people have re-derived it for a variety of different microscopic rules, doing very deep and very hard and very complicated kinetic theory calculations, none of which I even understand, much less would dare to duplicate. And the equation they got was exactly the same as the one we wrote down, okay? It's very similar to the situation in fluid mechanics. You can go from kinetic theory to the Navier-Stokes equation, And amazingly, you get an equation that was written down by a couple of guys in the 19th century who'd never heard of kinetic theory, had never even heard of molecules. Okay? And Juhai and I were working much the same way. We didn't know much, but we were able to leverage the few things we knew into the equation, which is uniquely the only equation that can describe a moving flock. Okay. And of course, the way you do that, there's this phrase that I love, you bury your ignorance of what's going on microscopically in a few phenomenological parameters. Then we solve this model. It turns out that, of course, birds aren't smarter than nerds. This continuum model has some non-equilibrium aspects that enable you to get around Mermin-Wagner theorem, and that's associated with this breakdown of linearized hydrodynamics that I'm going to describe. So that's where I'm going to go with this. Okay, so let's start out with the Vicsek model. So in Vicsek's model of bacteria is a very simple object. It's a point, and it's a point that carries an arrow. That arrow, you can think of it as the long axis of the body of a long bacteria, or any other way you want. It's an arrow that tells the bacteria which direction it's going to move on the next time step. Okay? These bacteria are really simple. They're all identical, and they all move at the same speed. Where did I put the speed in here? Yeah, they all move at the same speed, v0. All they change is their direction. Okay? And to make the model really simple, Vicsek made it a discrete time cellular automaton, which is just a fancy way of saying that each bacteria, in addition to carrying an arrow, carries a watch. And the watch is more like an old-fashioned Victorian clock. Instead of the second hand moving around continuously, it clicks discretely every second. All the watches are synchronized. Every time the watch clicks, each bacteria identifies its neighbors, and it does that in the simplest possible way. It draws a circle around itself of some radius r, which you can choose to be 1. You can choose your unit of length to be that radius. Anybody who's inside that circle is a neighbor. Everybody who's outside that circle is ignored. Okay? You take everybody who's inside that circle, you take, and you can see not only the bacteria, but you can see the arrows they carry. You take the vectors along the arrows they carry, add them all up, divide by the number of neighbors you have, which will be different for different bacteria, and that defines an average direction. The direction you're going to move until the next time your watch clicks is that direction plus a random noise. And the random noise is just there to reflect the fact that you're not perfect. You may not observe them perfectly. You may observe them perfectly, but not quite move in the same direction. Okay? And then, and everybody does this simultaneously. So everybody sees the arrows that everybody's carrying, picks their new direction, adjusts their new direction, and then until the watch clicks again, they just walk in that direction at the speed v0. The watches click again, and the process starts over. Okay? So the parameters of this model are the speed v0. You could take the radius r to be a parameter. You could just say I'm always going to define my unit of length to be that radius. So then you just have v0 and the density, how many of these guys per unit radius squared there are, and the statistics of the noise. So I'm going to take the statistics of the noise to be 0 mean. So that just means that if you make a mistake, you're equally likely to turn to the left or turn to the right. And then there's only one parameter left, which is the variance of the the noise also is going to have no correlation between neighbors. So the mistakes I make have nothing to do with the mistakes that my neighbor makes. And it's going to be uncorrelated from one time to the next. So if I make a mistake to the left on this step, on the next time step, I'm equally likely to go left or right. Okay? If you impose all those constraints, then the only parameter you have left is the mean squared amplitude of this noise, of this mistake. That plays a role very similar to the role of temperature in a thermal equilibrium system. Okay? So I've given this in some detail just so you have a concrete idea of the sort of system I'm trying to describe. So before I go on, are there any questions about this model? Anything anybody wants to hear about? Probably a lot of you know more about this model than I do. Okay. You can, of course, imagine putting a lot of bells and whistles on this model. You could imagine allowing the speed to have some fluctuation as well as the direction of motion. You could imagine making the creatures pay more attention to the ones who are in front of them than the ones who are behind them, or vice versa. You know, there's a lot of bells and whistles you can put on this. But the important features of this model are it's local. You only interact with a few nearest neighbors. It's noisy. And the dynamics is rotation invariant. If I took a snapshot of this, rotated it by 30 degrees, and then ran the algorithm again, it would evolve exactly the same way as it did before, except all the vectors would be rotated by 30 degrees. So it's completely rotation invariant. Those are the features that I think are important. Okay. No, in this model there's not. But, okay. one of the bells and whistles you can imagine putting on this is including some hardcore repulsion. So saying you pick your direction like this, but then you might modify it if moving in that direction brings you too close to one of your neighbors. You could also imagine an attractive interaction. You don't want to get too far from your neighbors. Now, there's a lot of bells and whistles you can put on this, and people have played games with all of those. As long as all those bells and whistles are short-ranged in space and time, I think those systems are all going to be described by the same hydrodynamic model as this system. Okay, so there's nothing about the hydrodynamic theory I'm going to write down that's particularly rooted in this system. I just want to make sure everybody has at least one concrete idea of the type of system I want to imagine. Okay? So that's the Vicsek model. All right. So Vicsek set this up on the computer. He simulated it. And something happened that at first... Oh, there's one other feature of this model that I didn't emphasize, so I should. It's two-dimensional. The motion is all happening in 2 dimensions. You can, of course, simulate models like this in 3 dimensions and higher, and that's been done as well. But for now, I'm going to talk about the 2-dimensional model. That was the first thing Vicsek looked at, the first thing he simulated. And what he found was that as long as the noise isn't too big, as long as you're only making small mistakes, you can start with a completely random configuration. You can just throw your bacteria at the screen like an abstract expressionist painter, splatter them at random with the arrows all pointing in random directions, run this. So when you do that, notice an important concept in this system is the average velocity, by which I mean you just sum the velocity vectors for all the bacteria and divide by the number of bacteria. And obviously, in the initial state, if you plunk down enough bacteria, that average velocity is going to be 0. Yeah, question? Good question. There's a lot of different boundary conditions you can imagine. I'm guessing that you're asking that because you're wondering what keeps them from just spreading out and becoming infinitely diffuse. Yes, you need some kind of boundary conditions to constrain that. Vicsek originally did the simulation with periodic boundary conditions. Okay, so if you imagine the flock being confined to this rectangle, if they flew out the top, they reappear at the bottom. If they fly off the left, they reappear at the right, and so on. Yuhai later did some simulations where we did mixed boundary conditions. We have reflecting boundary conditions at the walls and periodic boundary conditions at the top and the bottom. The important thing is to set up boundary conditions that allow the flock to move coherently in one direction. Otherwise, if you have rigid walls, then you have to set up some kind of giant vortex, and that's a state I don't want to talk about. Although I think you can understand that with the hydrodynamic theory too, but it's just a different state. To keep it simple, imagine that we're using one of these 2 types of boundary conditions that allows the flock to just move freely in one direction. Good question. By the way, I encourage everybody to speak up, shout out, even the invited speakers, even the old guys can do that. Okay. So anyway, so Vicsek runs a simulation and something happens which, if you don't know the Mermin-Wagner theorem, if you haven't been trained as a statistical physicist, doesn't seem surprising at all. You run this algorithm, the algorithm makes the guys tend to move in the same direction, so guess what? After a long time, they all wind up moving in the same direction. They go into a state where the velocity is non-zero. The direction of the velocity cannot be predicted a priori. And if you took this system, re-scrambled it, ran the simulation again, you'd get the average velocity having the same magnitude, but the direction being some completely different direction, because the underlying dynamics don't pick out a special direction. Okay, and that's what we mean by a spontaneously broken continuous symmetry. So at this point, if you don't know statistical mechanics, you just yawn. Right? If you do know statistical mechanics, particularly if you have Vicsek standing in front of you sort of shaking this fact in your face, you realize that your training tells you that this should be impossible because it's a 2-dimensional system. Okay. So this seems to violate the Mermin-Wagner theorem, and that's the mystery that got me into this whole business. Okay, so why is that astonishing? Well, to illustrate this, I want to describe an experiment that's been done, I guess, about 60 times now by the American Physical Society. Every year, you gather all the condensed matter physicists in the United States, and many from outside the United States, and you send them all to a city that none of them have ever been to before. Okay? And you have these huge, giant sessions in these gigantic hotels with these huge lobbies, and at the end of the last session of the day, 20,000 physicists, it's a terrible sight, gather in this giant lobby and try to decide where to go to dinner in a city that none of them has been to before. Okay? So how do you do that? Well, you're not animals, right? You're not going to just start swarming around like ants in some random direction. You're going to choose a direction that you're all going to go in to look for a restaurant, right? So everybody stands stationary on the floor of this giant lobby. It's a 2-dimensional system. It's very large, and tries to choose a direction to move in. Okay? So every one of the physicists points in a particular direction initially, right? But you're perfectly agreeable. Furthermore, you don't know where you particularly want to go. No one direction is preferable to any other. So if you see the physicists around you are pointing in different directions, you align yourself to the average of their directions. Okay? And you constantly update that because they're constantly changing their direction of pointing to align with their neighbors and so on and so on. You recognize what I'm doing here. I'm describing the Vicsek algorithm, right? With one exception. You're physicists, you're smart, you're not going to move until you decide on a direction to move, okay? So these are, I like to call these pointers rather than movers, or pointers rather than flockers, okay? So you stand stationary and you try to point in the same direction as your neighbors, okay? And what happens? Has anybody here ever been to the American Physical Society March meeting? Show of hands, anybody? Okay, so you all know what happens, right? You never get dinner. The reason you never get dinner is you never wind up with everybody pointing in the same direction. And the reason you never get everybody pointing in the same direction is the Mermin-Wagner theorem, okay? So a better way to get the Mermin-Wagner theorem is just to try to calculate, if I look at, calculate what's the mean squared fluctuation in the direction somebody in this huge gathering of physicists is pointing. You know, what's the fluctuation in that direction, the mean squared fluctuation in the angle. Turns out if you calculate that, and I'll go through roughly how you do this calculation in a few minutes, you find that in this two-dimensional system, that mean squared fluctuation goes like the logarithm of the linear extent of this system, okay? The coefficient in front of that is proportional to the mean squared error that you make in aligning with your neighbors. So you might think, all these people have PhDs, they're pretty smart, that mean squared coefficient is going to be pretty small, but it's not going to be 0. If you have a number that's not 0, multiplying a logarithm of L, and L is going to infinity, and this is a very big gathering, so it's pretty damn close, that product is going to go to infinity. Okay? If I made this an actual infinite flock, at some point as I made the flock grow, no matter how big that how small that coefficient in front is, this mean squared fluctuation is going to get to be bigger than 360 degrees. And people are going to be pointing in all possible directions with equal probability. And so you're not going to align. If you took the sum of all the vectors of all of these pointers and divided that by the number of pointers, you'd get 0 because the vector would be uniformly distributed around the circle. Okay? So that's the Mermin-Wagner theorem. Okay? And so another way to say this is you take a bunch of people, put them in a featureless environment where no special direction is picked out, and ask them all to point in the same direction, they can't do it. Take the same people, have them make the same errors, give them the same range of interaction, and tell them all to walk in the same direction, and they can do that with no trouble. When you put it that way, it's pretty amazing, right? And so that difference, why you can all walk in the same direction, but you can't all point in the same direction, that's what I want to understand. Okay? Before I do that, I want, for the benefit of those of you who haven't seen this, and also because it gives us some insight into why flockers are different from pointers, is to explain where this comes from and why it's special to 2 dimensions. So let's do that. So the first thing to realize is that this dynamical rule for pointers, where everybody's standing still, actually corresponds to, well, this isn't going to help you very much if you're not a trained statistical mechanic. If you are, this is going to seem great. That rule is essentially a Monte Carlo algorithm for an equilibrium 2-dimensional XY model, which is a model for ferromagnetism in 2 dimensions. So if you had a one atom layer thick piece of iron, it's a model for how that might magnetize. Okay. Okay. So that what might be more useful to you is to realize that that algorithm is also a type of noisy diffusion equation. And to illustrate that, let me just take that algorithm. So the algorithm said that the angle, the direction you're going to point in, or the angle you're going to make at time t plus 1, is the average of the angles your neighbors make at time t. Let me just subtract the angle you yourself made at time t from both sides of that equation. Okay? If I do that, on the left-hand side, what I have is the difference between my angle at time t plus 1 and my angle at time t. That's like the time derivative of theta. Make sense to everybody? Okay. On the right-hand side, I have the difference between the local average of the angle and the angle at the center, right, at the middle, where I am. Okay? Well, what is that? Well, if you go back to your E&M course, when they taught you how to numerically solve Laplace's equation, this thing is a discrete approximant to the Laplacian. Okay? And you can work that out. If you just imagine putting the points that your neighbors are located at the 4 vertices of a square, and you're in the middle, and you calculate this difference from a Taylor series, you'll find out it's just a Laplacian. Okay? I won't go through that arithmetic. That's your homework assignment. Okay? It's pretty simple to show. It's a fact that's been used millions of times in millions of numerical solutions to the Laplace equation, and it's just true. Okay? So effectively, what that dynamical rule says is that if I have a local region where the angles are big, they're going to spread out diffusively. But on top of that, I've got noise. So how does a noisy diffusion equation like this behave? And what's special about so you notice I've written this in 2 dimensions. In 3 dimensions, I would just have the extra components of the Laplacian. Okay. Any questions about this? Okay. So this statement that this model is equivalent to a noisy diffusion equation is true in any dimension. Okay, so let's think about what it implies. Well, let's think about what we know about the diffusion equation. Okay. So there's 2 important things we know about the diffusion equation. The first thing is it's really, really slow. Right? When you had coffee this morning, or if you had coffee during the lunch break, if you have it with milk, you didn't pour the milk into the coffee and then walk away and wait for the milk to diffuse through the cup of coffee. If you did that, you'd be coming back to get your coffee tomorrow and it would be ice cold. Right? Diffusion is a very slow process. In a sense, it's infinitely slow, and in the following sense. If you create a localized displacement at t equals 0 in a field that obeys the diffusion equation, then at a much later time t, that disturbance will have spread out over a region whose width grows like the square root of time. And it's really easy to see where that square root of time comes from. A time derivative of theta is just like theta over a time. A Laplacian is like theta over a distance squared. So time goes like distance squared, or distance goes like the square root of time. Characteristic property of the diffusion equation. Okay? So any disturbance you create is going to spread out like the square root of time. That's the first thing we know. The second thing we know is that the diffusion equation conserves the thing that's diffusing. Okay? If you look at the time derivative of the volume integral of theta, if I turn off the noise, then it's just the volume integral of the Laplacian of theta, and that's a surface. That can be written by the divergence theorem as a surface term. The only way you can get stuff out of a given volume is for it to escape through the surface. Otherwise, the total amount of stuff in that volume is conserved. Okay? So things grow very slowly, and stuff is conserved. The combination of those 2 things tells you where the Mermin-Wagner theorem comes from. Yes? It's characteristic of the dynamics. I guess the fundamental answer to that is that the underlying dynamics are rotation invariant. Okay? So for theta to not be conserved, you'd have to have all the angles moving in the same direction in some region, and why would they do that? Right? You're always, if I always adjust myself to the average of my neighbors, then you can check it out. You can just do the numerical experiment of looking at what happens for a few neighbors interacting with each other. The sum of their angles always winds up being 0. It's like, if I respond to the average of my neighbors, it's like I'm passing my angle over to the next guy, but it's just an intrinsic property of the dynamics. Okay? And it's a consequence of the symmetry, which is a good point. Okay, so my angle field obeys a diffusion equation. So let's ask what would happen if we turned off the noise. So we just have the angle field obeying the diffusion equation. And let's make it really simple. Let's assume at t equals 0, we started with a flock where everybody was moving in the same direction. I'll call that direction theta equals 0. And one lone bird sitting in the middle of the flock is going off in a different direction, and the difference between his direction and the direction of everybody else is theta sub 0. And now we're going to run this algorithm. What's going to happen? Well, at some much later time, the initial error is going to have contaminated, spread out over all the birds within a distance of or proportional to the square root of time of where the original bird was. Or the original point. I shouldn't call this a bird. I should call this a pointer, because we're talking about pointers here. Okay. So everything within a distance square root of time of the original pointer is now going to be making some mistake. Okay. Everybody outside is still going to be going in the same direction because there hasn't been time for the information to diffuse out to them. Okay. So all these guys are going to be making mistakes. What's the typical size of the mistake they're going to make? So now here's where we use the conservation. The sum of all the errors that all these guys inside this spherical or circular drop make has to be the same as the initial error, because the diffusion equation conserves. Okay? So the error that any one of them makes is the original error, which is now the sum of all of the errors, divided by the number of birds that are making mistakes. I'm crudely assuming here that they're all making the same mistake, which is of course not true, but for an order of magnitude estimate, this is okay. Right? So theta of t is going to go like theta naught over the number of birds in this region. The number of birds in that region depends on time, because the region is growing. How does it depend on time? Well, the radius is growing like the square root of time, so how is the number growing with time? Well, I guess I'm making it a little obvious because I've written the answer. The number is going to grow like the square root of time to the power d, where d is the spatial dimension of this system. So in 2 dimensions, it'll be t to the 2 over 2 it'd be growing like t. In 3 dimensions, it'll be growing like t to the 3 halves. In 4 dimensions, if you can imagine that or you can simulate that, it'll be growing like t squared, and so on. Okay? So what this means is that the typical error a bird that's making an error at time t makes is falling off with time, like time to a power, and that power depends on the dimension of space. Okay? This is where the dimension of space comes in and starts playing a role. And you can see how it works. The bigger d is, the bigger this exponent is, and the faster the errors decay. Is that clear to everybody? In a higher dimension, the errors are going to decay faster. In a lower dimension, they're going to decay slower. Now, what happens in the real algorithm? In the real algorithm, you don't just start with you don't just have one mistake that then just spreads out and eventually goes away. While that's spreading out, you're constantly making more and more errors. Okay? So let's think about what happens in the full algorithm. Okay? So let's imagine a flock whose radius is r. Okay? And we started at t equals 0 with everybody, say, moving in the same direction. But now everybody's making mistakes. Okay? So until a time that grows like the radius squared, those mistakes are not going to have an opportunity to diffuse to the edge of the system and escape. So you're not going to be able to reach some kind of steady state until this time, because that's how long it'll take for the errors that are made in the center of the flock to get all the way to the outside. Okay? Is that clear? So during that time, every single pointer, I'm calling them spins, but every single pointer in that flock is going to make a total number of errors that's proportional to this time. So it's proportional to the radius squared. Okay? So there are a lot of errors because it takes a long time for the information to get out of the flock. There are also a lot of errors because there's a lot of critters making errors. There's a number n of critters making mistakes. That number n grows with the radius, like radius to the d power, and there's the dimension of space coming in again. Okay? So let's ask, what's the root mean squared error per spin in this flock at the time it settles down to equilibrium, which is this time? Well, if you have a lot of random errors which you add, okay, the total number of errors that are made are the number of birds making errors, which is r to the d, times the number of errors each one makes, which is r squared. So that product, the total number of errors that are made before we equilibrate, is r to the power d plus 2. Okay? So the root mean squared value of the sum of all those errors is just the square root of that. So it's the square root of r to the d plus 2. That error is divided over all the pointers in the flock. How many pointers are there? R to the d. So the root mean squared error per pointer is the square root of r to the d plus 2 divided by r to the d. I'm literally just counting on my fingers to emphasize that this is a fairly simple calculation. Okay, so hopefully this looks simple to you. Okay, are there questions about this? Okay, it's really literally just this simple. Okay, well, we can just take this ratio and say that that ratio is the typical error, typical fluctuation in the direction a given pointer in this flock is pointing. If we do that, we find that this ratio goes like r, the radius of the flock, to the power 1 minus d over 2. There's a coefficient here, and that coefficient is proportional to how big each typical error is. Okay? But the important thing is its dependence on r. It goes like r to the 1 minus d over 2. And now the question of whether or not these guys can all point in the same direction, no matter how big the flock is, comes down to the question, as I take r to infinity, does this fluctuation get bigger or smaller? Does it go to 0? Does it go to infinity? Does it stay finite? And so what's the answer to that? Anybody? Sorry? Yeah, okay. Yeah, I know. I should have covered some of this stuff up. Okay. So now you see where the spatial dimension 2 plays a role, right? If d is bigger than 2, this exponent is negative. So as you go to bigger and bigger flocks, the typical fluctuation gets smaller and smaller. In an infinite flock, the order will be stable. Okay? If d is less than 2, for example, if d was 1, this power will be positive. The mean squared the typical fluctuation in the direction you point will go to infinity as the radius goes to infinity, and you won't be able to get infinite order. And in fact, to get back to the question about correlation length, if you said, what's the value of r at which this fluctuation gets to be pi, that would be a good estimate of the correlation length. And it would always be finite if d was less than 2. D equals 2 is the borderline case, and borderline cases are always tricky. But if you remember your calculus, you know that in calculus, whenever you get an exponent that's 0, that doesn't mean a constant, it means a logarithm. And by doing a slightly more detailed calculation than this, you can show that in 2 dimensions, this r to this power gets replaced with a logarithm, and so things still blow up in d equals 2, and that's the Mermin-Wagner theorem. That's it. It's really just a matter of counting on your fingers. Turning this into a theorem involved a lot of fancy mathematical footwork and epsilons and deltas, but basically the argument boils down to this. Yeah? Right. Well, no, but there's always, in a system of discrete particles, there's always one length, well, there's a lot of length scales you can define, but one length scale you can always define is the typical inter-creature distance. And that'll typically roughly play the role of the lattice constant. You know, figuring out what that microscopic length actually is a hard problem, but there's always something that can make this suitably dimensionless so that you can define a correlation length that really comes out to be in meters. Okay? All right. So that's the Mermin-Wagner theorem. So how do you get around this? You know, that's the question. And to answer that, Hai-Tu and I decided to look back historically because, okay, so first of all, let me step back. When I started thinking about this, I realized that there was no way I was going to be able to sit down and come up with an analytic solution to the Vicsek model. You know, I mean, it took Onsager and 100 years for somebody to come up with an analytic solution to the Ising model. The Vicsek model is much more complicated, right? So there's no way we're going to analytically be able to do anything with the microscopic model. Even if I could, that's one model, right? People in this audience have already come up with many variants to the Vicsek model, and it wouldn't be obvious a priori whether anything you said about the Vicsek model would apply to one of those other models. Right? So what we'd like to do is come up with an understanding of what features are general to this type of motion and what features are, well, we want to focus on what features are general to this type of motion. Okay, so historically, well, we felt, Hai and I felt that we were pretty much in the position that Navier and Stokes were in at the beginning of the 19th century. They wanted to understand fluid mechanics, right? And they recognized that they didn't really understand what's going on microscopically in a fluid. I mean, if you think about it, they had no theory of atoms and molecules in 1820 or whenever it was. They didn't even know that fluids were made out of atoms and molecules. I don't think that had been settled at that point. They didn't have statistical physics, right? I mean, Boltzmann hadn't even been born at that time, much less committed suicide. So they didn't have TVs, they didn't have computers, they couldn't do numerical simulations. You know, the situation would look pretty hopeless. Yet these two guys in the 1820s wrote down two very simple equations, which now in the 21st century are the equations that anybody who wants to study any fluid mechanics problem starts with in understanding fluids. And those are, of course, the equations that bear their names, the Navier-Stokes equations. I don't actually know how they came up with those equations, but I do know how we would come up with those equations nowadays. And so I'm going to describe that approach, and that's the approach that Hai and I were going to use to describe flux. Okay, so the first step is to forget about trying to keep track of all those millions and millions of discrete particles moving, each moving independently. Instead, use a continuum model. Okay, so we're going to take a phenomenological approach and we're going to treat this flock as if it's a kind of living fluid, an active fluid, if you like. Okay, and by fluid, I mean, we think of it as a medium that actually fills all space. So we're going to describe it, instead of describing it by discrete point particles, we're going to describe it by continuous fields. And the continuous fields we're going to use are the same continuous fields that Navier and Stokes used in fluid mechanics, namely the velocity field and the density field. So at each point in space, you imagine there's some fluid there, and it's moving at some velocity associated with that point in space, which can evolve as a function of time. And likewise, at each point in space, there's a certain number density of particles, which depends on where you are in space and can evolve with time. Okay? In the lecture tomorrow, I'll tell you how we know that these were the only fields that we needed for the flock. But for now, I'm just going to assert that these are the fields we're going to use to describe this system. You'll realize that in taking this approach, there are some fundamental limitations. A picture like this is absolutely nuts if you want to describe phenomena that happen on a length scale that's smaller than the typical distance between creatures. Because on that length scale, you can tell that there's a creature here, there's empty space here, and there's another creature there. There's nothing like a continuum. This approach only works if you're looking at length scales that are so large compared to the distance between creatures that it looks like they're a medium filling all space. Okay? Now you can call that a bug or you can call that a feature. I call it a feature because what this means is that there's absolutely no point in me including terms in my equation of motion that are unimportant at long distances. This enables me to throw out millions and millions, in fact, an infinite number of possible terms in my equation of motion. Just say they're not important in the range where this equation of motion even makes any sense. Okay? The buzzword for that is a gradient expansion. I'm going to write down equations of motion for these guys that are going to involve spatial derivatives and time derivatives, and I'm only going to keep the terms that involve the smallest possible number of those. Because every time you take a derivative, it's like dividing by a length scale. And the theory is only good at long length scales, so terms that involve lots of derivatives are going to be divided by very, very big numbers and are going to become unimportant. Okay? So I'm going to do a gradient expansion. I'm only going to keep low order space and time gradients. But everything I just said about length scales also applies to time scales. Okay? So that's the first simplification I'm going to make. I'm only going to keep low powers of space and time derivatives. I'm also going to assume that these fields don't fluctuate very much around their mean values. So there's some average density and there's some fluctuation around that. There's some average velocity the flock is moving at and there's some fluctuation around that. I'm going to assume those fluctuations are small and expand in those fluctuations. I'm only going to keep terms in the equation of motion that are important to low order in those fluctuations. That throws out infinite numbers of terms. Yes? No, you have to do more than what I'm going to describe. That's right. Okay, and although you can use these kinds of ideas, but you need to add another ingredient, namely that you're close to a phase transition. And I guess to be fair, I should say that you can actually address the phase transition with this model, but that's not what I'm going to try to do. I'm not going to look at it in a regime where it goes anywhere near a phase transition. What happens near a phase transition is that there is another length scale that's introduced, which is a correlation length, and if you assume that that's long, then you can extend this expansion and actually figure out what's going on.
So I was worried because here momentum in your system is not conserved.
That's right.
So in isotropic phase, you can't assume velocity as a Hydrodynamic variable.
It turns out that you can, or rather, to be more precise, it turns out that some components of the velocity are a hydrodynamic variable. Let me come back to that when I go on. It's right. This is a system. In a system where momentum is not conserved, a lot of people would reflexively throw this field out. Okay, I'm not going to do that because it turns out it's a hydrodynamic variable, or some of its components are hydrodynamic variables because of the broken continuous symmetry. But I'll come back to that. Okay. Anyway, so I'm going to expand in powers of space-time gradients. I'm going to expand in powers of fields, and then the thing that's really going to narrow this down is that whatever equation I write down had better respect the symmetries of the underlying dynamics. In particular, the underlying dynamics of rotation invariant, so these equations have to be rotation invariant. What that means mathematically is that if I take my equation of motion for the velocity, for example, and I rotate all the velocity vectors by the same rotation matrix, rotate all the position vectors by the same rotation matrix, which means I rotate all the spatial gradient operators by the same rotation matrix, then the equations have to remain unchanged. That's a huge constraint. So those are the constraints. Those are the things that the constraints that I'm going to apply in writing down my equations of motion. And then the question is, okay, so how do you write down your equations of motion subject to these constraints? And the answer is you just make them up. That is, you literally write down you say the time derivative of the velocity is everything I can think of on the right-hand side of the equation that satisfies all those rules. Now, when I've written this equation, I've taken some of those terms from the right-hand side over to the left-hand side, but the idea is time derivative of velocity equals stuff. That stuff has as few spatial gradients as possible. I'm only keeping terms that are important for small fluctuations in the field, and what was the other thing? And I'm respecting rotation invariance. Okay? And it turns out this is the only equation you can write down. There's actually some slight generalizations of this, but this is essentially it. Okay. By the way, I should say, if you apply this same logic to a simple fluid, you get where there's an additional conservation law, namely conservation of momentum, then you get the Navier-Stokes equations. There's nothing else you can get that satisfies all those rules. So the Navier-Stokes equations describe all simple fluids. These equations will describe all flocks. By all flocks, I mean all flocks in which the symmetry that's broken is, in which you break the symmetry by going to a state where everything is uniformly moving. Yeah.
Why is the following neighbors transport term and not in the 5-4 term?
Good question. Okay, let me answer that as I work my way through this. Okay, but that's an important question. Okay, so as I said, we just wrote these terms down by symmetry, but then if you look at them, you realize they have a simple every term in this equation has a fairly obvious physical interpretation. So let's look at this first one, alpha v. So if that was the only term in the equation, you'd have time derivative of velocity as alpha times velocity. Well, you've all seen that before. You probably all saw that in freshman physics, right? If you're trying to make a simple model for the motion of something on a substrate with which there's friction, you say there's some drag coefficient, and there's a frictional force on the particle that acts in the direction opposite its motion and is proportional to the speed. Right? So you'd say dTV is minus drag coefficient times the velocity. Okay? This is the aspect of these equations where the activity comes in, is the fact that I'm going to allow this coefficient alpha to be positive. If I was talking about a dead system, a system where there was no energy being put in to keep the system moving, alpha would be negative. You know, this would just be a friction term. You'd have dTV as negative some coefficient times v, and all the velocities would just decay exponentially to 0. But because the system is active, I'm going to allow this coefficient to be positive, right? I can move not only despite the friction with the surface, but because of the friction with the surface, right? Because I'm alive and I can provide energy. And the flockers are doing the same thing. I'm trying to think of a way to answer this equation that will simultaneously satisfy you and not confuse a lot of people in the audience even more. No, I'm not. I'm not trying to make an excuse for not answering. I'm just trying to think of a way to answer it. Right. Naively, you would think that this coefficient is positive if the individual creatures can move at a finite speed, and negative if they all just would come to rest in isolation. In reality, whether it's positive or negative depends partly on that and partly on collective effects. Right? And if there's a lot of disorder, that can effectively normalize this coefficient from positive to negative values. Right? So to make this coefficient positive, I'll get to you in a second, Erwin. I'm really not going to deliver on the thread I made this morning. I will answer your question, but just let me finish what I'm saying here. Except now I forgot what I was going to say. Ask your question. Maybe it'll come back to me.
From symmetry, all these coefficients you have, alpha, b, and whatnot, they can be arbitrary functions of this.
Mm-hmm. That's right.
Dynamic variable, and doesn't this mess up all the...
Yeah, that's right. So these equations are actually worse than they look, because what Erwin just said is absolutely true. This alpha could depend on the local density, so could beta. The pressure already does, so that's not a problem. These diffusion coefficients could, these lambdas could, and they all do, in fact, undoubtedly. Right? It's even worse than that, because they also all could depend on the local speed. Right? So furthermore, these equations already look bad enough. Right? But what I'm going to do is take these equations, allow these coefficients to depend on the local density and the local speed, assume those fluctuations in local density and local speed are small, Taylor expand up the wazoo, and finally get a system of equations with a finite number of parameters in them, and those are the ones I'm going to analyze. Okay. And you can do the same thing in the Navier-Stokes equations. Turns out in the Navier-Stokes equations, you only need to keep the rho equals rho 0 value of everything, and nothing depends on the speed because you have Galilean invariance. So it's a lot simpler. But you can actually take all that stuff into account. That is something that Juhai and I got wrong in our original papers. And if you want to see the first place somebody got it right, it was a paper that I wrote in 2012, which, if you count it up, was 18 years after we wrote down the original equations. But it turns out you can cope with that, and you do need to for certain things. But as long as you keep in mind that all these coefficients can depend on the local speed and the local density, these are the only equations you can get. Okay? So let's talk about these terms. So if you're alive and you're ordered, this coefficient alpha can be positive. So you can develop a local macroscopic non-zero speed. Now, of course, if this were the only term in the equation, you'd have dtv as alpha v, and v would grow exponentially with a time constant given by alpha. Eventually, the flock would be moving relativistically, and things would be very bizarre. And of course, that doesn't happen. You know, I can walk across this floor, but I can't walk across this floor at 100 kilometers a second. I can't even go as fast as Usain Bolt. There's some limit on how fast I can go, and that's what this second term represents. It's just a term that will make the speed saturate at some value where these two terms cancel. But if alpha is positive, the important thing is that that value will be non-zero. Okay? So there'll be some non-zero speed at which these two terms cancel, and that's the speed the flock wants to move at. Okay? So that term, any questions about that term? That's what that's supposed to represent. So that represents the preferred speed, takes into account friction, takes into account activity. Yeah? Aha. Yes. And that goes back to Julien's comment. Okay? If I look at the system on a Lloyd scale, there's nothing that says that the speed at which a given region of that is moving is going to be the same as the microscopic speed at which things are moving. To take an extreme example, if everybody's moving in a random direction, the mean speed of that droplet is going to be 0. But each creature can still be, you know, you can add up a bunch of vectors of constant length, of equal length, and get 0. Right? So even in the Vicsek model, where you might think the speed could only be whatever the V0 is in the Vicsek model, the magnitude of the speed can actually fluctuate. And so these coefficients can actually be finite, but non-zero. Yeah, that's a good point. So, you know, if you wanted to ask what are the values of these parameters for the Vicsek model, a naive guess would be that you have to choose alpha and beta such that the V0 that comes out here is the V0 in the Vicsek model. It's probably a good approximation if the noise is very, very small, because then the fluctuation effects are small. But as you get near the transition where the order is lost, it's going to be a very bad approximation. Okay. These are, I'm going to take this off. These are good questions, so keep asking. Okay. You may have to ask louder now, because the only way I can keep this microphone on is to take my hearing aids off. Okay. There we go. I have perfect hearing in this ear, so if you're on this side of the room, you'll be fine. If you're on that side of the room, you have to be louder. Okay, so that didn't even help. Okay, so that's what. So these terms essentially represent the fact that you try to move, but you have a limited speed at which you can move. Okay, this term is familiar if you've ever seen fluid mechanics before. If you've ever seen the Navier-Stokes equations, this term just says that if there's a gradient of the density, if I have high density on this side of the room and low density on that side of the room, there's going to be a force that's going to push me from this side of the room to that side of the room, so I'm going to accelerate in that direction. Okay? So this is just ordinary pressure forces. Okay? What else do we have? These terms, these first two terms are also terms that appear in the Navier-Stokes equation. You can think of them as diffusive terms. Okay? They just tend to make the velocity spatially uniform. And that's what's going to happen if you have creatures trying to move in the same direction as their neighbors with the same speed. That's going to make the velocity spatially uniform. So these things are related to whatever the aligning interaction is in the Vicsek model. Sorry, yeah. No, no, we're not. That's why I have a second equation here. In fact, and that's why I have a third equation here. Sorry. I probably should have presented these in the reverse order, and then it would have been clearer. Right. Yeah. So to close these equations, I need to specify what this pressure is as a function of density. And actually, getting back to Erwin's comment, all of these coefficients in this equation, lambda 1, lambda 2, lambda 3, alpha, beta, d1, d2, and so on, they can all be functions of the density. In principle, I need to specify all those functions. Now, in practice, since I'm going to assume that the fluctuations in the density and the speed are small, I can get away with expanding Taylor expanding those in those fluctuations and keeping only the first few terms. In many cases, I can get away with just keeping the leading order term and treating them as constants. Obviously, for the pressure, I can't do that. I need to allow the pressure to vary to create these pressure gradient forces. Okay? So these terms just reflect the tendency to follow your neighbors. Right? So it's a bit peculiar. To get back to Julien's comment, this term tends to make the flock keep moving, but it doesn't make it coherent. These diffusive terms are necessary to actually make all the directions of motion line up. If you only had these terms, you could wind up in a bizarre state where everything is moving at the same speed but in a different direction. And that would macroscopically have an average speed of 0. So to make something with an average speed of non-zero, you need these diffusive terms as well. This F is a Gaussian white noise that just represents the mistakes the creatures make. And then we have these terms up here. Okay? The first term will again be familiar to those of you who have seen the Navier-Stokes equation. This is sometimes, this combination dTV plus V dot grad V is sometimes called the convective derivative. And what this is the rate of change of the velocity that's seen. Imagine you're looking at a rapidly flowing stream and you look at a boat being carried down by the current. Okay? Actually, let's imagine the following situation. Let's see. Is there an eraser? Right, no, that's not an eraser. Yeah, it is. Okay. Okay, so here's a stream. There's a waterfall. There's a guy in a boat. Okay, and the stream is flowing steadily over the waterfall. Okay, you're standing here on the shore, looking at the water as it goes by. Okay. To you, the stream is flowing steadily, so to you, the velocity doesn't seem to be changing, right? dTV is 0. So you might think that somebody going by you in a boat is not going to experience any acceleration because the velocity at that point is 0. But of course, the guy in the boat is going to experience some rather nasty acceleration because he's going to eventually be over here where the water is getting ready to rapidly go over the waterfall, right? So the acceleration measured by this guy is different from the acceleration measured by this guy. This guy on the shore says it's 0. This guy in the boat says it's non-zero. And the difference between those two accelerations is the difference between dTV and dTV plus V dot grad V, which is the rate of acceleration of this boat. He's accelerating because he's moving at a speed V, the speed of the current, from a place where the velocity has some small value to a space where the velocity has some larger value. And the rate at which he's accelerating is proportional to his velocity times that gradient acting on the velocity itself. Okay? So this term is very familiar. It's just a convective derivative, except I have parameter lambda 1 there, which does not have to be 1. And why is that? Well, the parameter lambda 1 in the Navier-Stokes equation has to be 1 because there's Galilean invariance. Right? The equations of motion seen by the guy in the boat have to be the same as the equations of motion seen by the guy on the shore. So that means you can't tell the difference between an acceleration that comes from the fact that you're moving relative to the shore and an acceleration that comes from the fact that the velocity is actually changing at a fixed point relative to the shore. Okay? But that's only true in a Galilean invariant system. If you have a special reference frame, like the surface over which the creatures are moving, then you don't have Galilean invariance. So there's no symmetry that tells you that you can't tell the difference between acceleration due to the fact that you're moving and acceleration due to the fact that the velocity at this point in space is changing. You can, in a non-Galilean invariant system, tell the difference between those two things. So this coefficient lambda 1 does not have to be 1. But it also doesn't have to be 0. So it's there. Okay? So that's a nonlinear term that's necessarily in the equations of motion. Now, once you start playing that game, you realize that this is not the only combination of velocities and gradients that transforms like a vector. And I should say, the role of rotation invariance in this problem is that when you write down dTV equals stuff, the stuff has to be a vector because dTV is a vector. Okay? Furthermore, the vector that you write down because of rotation invariance cannot be one that you pick. I can't put a unit vector north, unit vector south, east, or west on this side of the equation. I can only put down things that the system picks by itself. And that means either velocities or gradients, and that's it. That's all I have. So this combination of velocities and gradients transforms like a vector. 2 velocities and 1 gradient dotted in indices contracted in just the right way to make something that transforms like a vector. Once you realize that that's the game, you ask, what other quantities can I make with two velocities and one gradient that transform like a vector? And you realize you have this combination, velocity times divergence of velocity, and this combination, the gradient of the speed squared. All three of those have two velocities and one gradient operator, and they all transform like vectors. Okay? These also have simple physical interpretations. This one I call crunch anxiety. Okay? If div dot v is non-zero, that means things are either converging or diverging. Okay? So imagine you're driving along a very wide highway and you see cars converging up ahead of you, right? Depending on whether you're a coward or a daredevil, you're either going to accelerate towards that because you want to get in on the fun, or you're going to stay back because you want to avoid the accident. Okay? You don't know a priori which one of those you're going to do, so you don't know the sign of this parameter lambda 2, but you can pretty much guarantee that you're going to have some reaction to that. And so there's going to be a term like that. This term plays the same role with speed. You're driving along a highway and you see everybody ahead of you is going 200 kilometers an hour, and everybody behind you is going 50 kilometers an hour. If you're chicken, you slow down to get with slow folks. If you're bold, you speed up to get with the fast folks. And this term just represents that. They're independent. You could imagine them being related to, both arising from the same microscopic interaction, but there's no symmetry that says that they have to be related in any way. Yeah. So it should be emphasized, if you tweak one aspect of any microscopic model, you probably change all of these parameters. And some of them are probably correlated in some way. That is, if you make the system stiffer, you increase the pressure forces, and you probably also increase lambda 2. But to say anything more precise than that is certainly beyond my abilities. But that's the sort of information you can get out of some of these kinetic theory approaches. But from a symmetry argument, these guys are independent parameters. Okay. Any other questions? All right. Yeah. Say that again? Because I'm trying to write down terms here that are analytic in the velocity. You could question that. It really doesn't much matter because the important place that we're going to be expanding these equations around is a state of non-zero velocity. Right? So really all I have to do is assume that everything in here is analytic near that point. I would be surprised though if you had a gradient of the magnitude of velocity, but you might be able to cook up a model that does that. But it doesn't really matter because you're not expanding around zero velocity, you're expanding around some finite velocity. Okay? All right, so that's an equation of motion for the velocity. As has already been noted, to close that equation you need to specify an equation of state. In principle that has infinitely many parameters, but it turns out that only the first two matter. Okay? That is the first two coefficients in a Taylor expansion of the pressure around in fluctuations around the mean density. Okay? So we have some parameters hidden in there. We have the parameters explicitly displayed in this model, all of which could be functions of density and speed. So they themselves can be parameterized in terms of the coefficients in their Taylor expansions. We also have parameters associated with the noise. Its mean is going to be 0, but it has some variance that'll have associated with a noise strength delta. What else do we have? To close the equations, we need an equation of motion for the density since it enters the equation of motion for the velocity, and that equation is really simple. It's just bird conservation. This just says that birds are not being born or dying on the wing. So if I want to lower the number of birds in this volume, birds have to fly out. And that's all this equation says, and you've all seen that equation a million times. I don't have anything else to say about it, except for the fact that it couples velocity to density. In fact, it couples velocity to density in much the same way that velocity and density are coupled in a compressible fluid. And one of the things you get out of these equations is you get something like sound waves propagating through the fluid. They look a bit different because the state they're propagating in is anisotropic, but they are essentially sound waves. Okay. Any questions about these equations? You're not supposed to understand what these equations imply yet. Like many equations in theoretical physics, you can write them down, but it doesn't mean you understand anything until you start trying to figure out what they imply. Yeah? Can you explain again the meaning of the lambda 3 term? So if lambda 3, let me get the signs right. So if lambda 3 is positive, and I pull this over to the right-hand side, that means dTV will be negative if the gradient of speed is positive. Okay? So that would say that if I'm here and up ahead of me things are moving faster than I'm moving here, I'll decelerate. Okay? I don't know that lambda 3 is positive. It might be negative. That would mean that if things are moving faster ahead of me, I'll accelerate towards them. Whether, which of those cases happens depends on the psychology of the creature, or to put it in another language, on the microscopic rules of the motion of the flock. If I don't know the microscopic rules of the motion of the flock, I can't determine what that is. If I do, but I'm not willing to do the horrible kinetic theory calculation, I don't know what that is either. And to be a bit skeptical, even if I do the horrible kinetic theory calculation, there's no guarantee that it's actually right, because all kinetic theory calculations involve uncontrolled approximations, and you don't know how good they are in this context. But anyway, so I know on symmetry grounds that there should be a term like that. I don't know what its sign is. Okay. So there's a lot that I don't know in these equations. It turns out very little of it actually matters. Okay. I can bury my ignorance in these parameters. Okay. Yeah?
But isn't the grad v squared term included in the v scalar grad v term? That the v scalar grad v term has a grad v squared and a v vectorial grad.
You can write this as this plus something else, right? But you cannot write this as that. Right, it has an extra piece. So I could either choose to write that extra piece plus this, or I could choose to write this whole thing plus this. And let's talk about it afterwards. They're equivalent. I could do what you want to do, and then I could reorganize the equation and still write it this way. Okay, I'll show you afterwards. It's a little bit too much algebra to do on a blackboard in front of all these people, but yeah. Yeah. Well, there's really no symmetry information here. We're not assuming anything about the equation of state except that it's an analytic function of rho. Oh, good question. The answer is it could. Right? It's going to turn out that that doesn't play a crucial role because the fluctuations in mod v turn out to be small. Okay. The fluctuations in density also turn out to be small, but they affect the hydrodynamics of the problem, so we need to keep those. But yeah, no, in the full calculation, especially in the full calculation I did in the 2012 paper, I kept that possibility as well. And it adds some parameters. I believe those parameters wind up being irrelevant to the final answer. They don't affect the long wavelength hydrodynamics. But you could imagine situations in which they mattered if you had shock waves or something. Okay, yeah. What is the source of the noise term? Mistakes. I'm sorry? Are you asking, does the force satisfy momentum conservation? No. So if everybody in this room is walking along and I'm trying to follow my neighbors, but I make a mistake, right? So you're all walking that way and I make a mistake, so I step off a little bit to the side. I've changed the momentum of the whole system by doing that. And I'm allowed to do that because I'm interacting with a substrate. You say, how can I violate conservation of momentum? Well, I haven't. I've actually transferred that momentum to the Earth, but the Earth didn't respond because it's big. Right? So, I'm assuming the background medium has no dynamics of its own. That it's basically static because it's big and it's heavy. Right? And once I do that, then the noise can be non-momentum conserving. There are actually lots of terms in this equation that are non-momentum conserving. That term is non-momentum conserving. Right? As you know, because if I made it negative, it would be a friction term. So once I violate momentum conservation in one term, I'm allowed to violate in all the terms. And so I violate it here. And that, by the way, that turns out to be really important. If I made this noise conserving, I would get very small fluctuations in the velocity. And there'd be no question of ever worrying about something like the Mermin-Wagner theorem. It's the fact that this noise is non-conserving that makes it look like this problem might obey the Mermin-Wagner theorem. But it turns out you're able to get around it. But the fluctuations are much bigger than they would be if this was a momentum conserving noise, but it's not. Okay? All right. So let me move on. So we have these equations, and now the question is, what do you do with them, right? And if you look at these equations for a few minutes, you'll realize this is the perfect storm of equations that you might have to deal with, right? First of all, they're partial differential equations, right? And partial differential equations are harder than ordinary differential equations. Secondly, they're stochastic partial differential equations because you have a noise in it. And thirdly, and this is the real killer, they're nonlinear. There are non-linearities explicitly displayed here, right? These are v squared terms. There's a v cubed term. There's a v squared term there. Oh, sorry. I should have said something about this term. This term has no analog in the Navier-Stokes equation because it violates Galilean invariance. If you went to a moving frame, this term would change. But we don't have Galilean invariance here, so we're allowed to have a term like this. What this term does is it makes velocity diffuse along the direction of motion faster if d2 is positive or slower if d2 is negative than velocity diffuses perpendicular to the mean direction of motion. There's no symmetry that says that can't happen, so it probably does. Okay. So anyway, hard equation, a stochastic nonlinear partial differential equation. In fact, two of them. So what do you do with them? How do you deal with that? Well, I'm going to tell you in detail how you deal with that tomorrow, but for today I'm just going to summarize the results, and then I'm going to give you a hand-waving argument that gives you the same answer. Okay. So it turns out you can actually analyze equations like this because there's an equation of much the same structure that has been studied for 200 years, namely the Navier-Stokes equations. If you want to study the thermal fluctuations of a fluid, you write down the Navier-Stokes equations, which look like this with a lot of the terms erased. If I erase the lambda 2 and the lambda 3 term, the alpha and beta terms, this d2 term, if I make the noise momentum conserving, what else do I have to do? And make lambda 1 equal to 1, these become the Navier-Stokes equations. People have studied the Navier-Stokes equations and in particular studied the effect of the nonlinearity associated with this convective term for a long time now. We understand how to do that. So once Yuhai and I got these equations, we realized we were home because we could just sort of copy what those guys had done, make the appropriate changes because the equations are different, and figure out what happened. And when we did that, here's what we found. We found that there was a kind of negative feedback in these systems. When you turn on the noise, they start fluctuating. Those fluctuations grow. Those fluctuations actually enhance the diffusion constant. In fact, it's very peculiar. It turns out that in the moving state, there are different diffusion constants for motion diffusion along the direction of motion than perpendicular to it. That's basically just coming from this term. Okay? It turns out the coefficient of diffusion along the direction of motion doesn't change much due to the fluctuation effects, but the coefficient of diffusion perpendicular to the direction of motion does. In fact, not only does it change, but in the presence of fluctuations, it's driven to infinity. That growth of diffusion, remember, the origin of the fluctuations that led to the Mermin-Wagner theorem was that diffusion was too slow. This mechanism, this nonlinear mechanism, makes diffusion faster, albeit only in one direction. That enhancement of diffusion enables you to get rid of errors faster, and that's what stabilizes the order in 2 dimensions. So it's a kind of negative feedback. The fluctuations are giving rise to an effect that's stopping the fluctuations from getting big enough to destroy the order. Okay, so very peculiar. We actually were able to come up with a scaling law for how the effective diffusion constant perpendicular to the motion depended on the size L of the flock. It went with a certain exponent, which turns out to agree with simulations. This phenomenon of a diffusion constant blowing up in the presence due to fluctuations in 2 dimensions was already known about in the Navier-Stokes equations, but in our case it's much, much stronger. And in our case, it makes possible this actual ordered state of the system. Okay, so that's what we found. And as often happens, after you do a fancy calculation and you get an answer, and you see the structure of the answer, you realize you should have been able to guess this just by waving your hands. And so in the last 10 minutes, what I'm going to do is give you a hand-waving argument that gets you to this result. Okay, so let's go back to that cartoon I drew when we were talking about the pointer problem, okay, and ask, we've got a flock of a certain size, and how does information spread in that flock, and how do errors accumulate? Okay, so imagine a time. How do I do this? Yeah, let's. Let's start with an individual bird at the center of a flock, and ask, after a time t, how many birds will have been affected by that? And let's assume that the dynamics are the same as the dynamics of the pointers, where everybody's standing still and just pointing. Okay? Well, if that's the case, then after a time t, everybody within a distance the square root of t of the original bird will have been affected by his fluctuations. Okay? So let's think of that collection of birds, the birds who were affected by the original bird. I'm going to call that collection the blob. And let's ask, how far is that blob going to move relative to the motion of the whole flock in that time t? Okay? Well, because of the errors that are made inside that blob, it's not in general going to be moving in exactly the same direction as the rest of the flock. Okay? So let's think about what that means. If you've ever been on a highway and noticed that the person in the car next to you is texting or talking on their cell phone or combing their hair, so they're not paying attention to their driving, you'll typically find that they're doing a pretty good job of keeping up with highway speed. They're moving at the same speed as you are. So if they were off to your right 10 seconds ago, they're probably still off to your right. What goes wrong is that they start to drift into your lane. Okay? And that's a consequence of a really simple piece of geometry. If you want the difference between a velocity vector in that direction and a velocity vector in that direction, and these both have the same length v0, that difference is, if this angle is small, almost exactly perpendicular to v0. Okay? And you can just see it's just geometry, right? As this angle goes to 0, that angle goes to 90 degrees. Okay? So when you make errors in the direction you're moving, and we're imagining that this blob is making a small error, so it's moving in a slightly different direction than its neighbors, relative to the rest of the flock, it's moving up at the same speed as the rest of the flock, but it's moving laterally from side to side at some speed. Okay? How fast is it moving? Well, we can estimate that by the hand-waving argument that I gave earlier. Okay? The typical speed it will be moving at laterally will be this speed v0 times this typical angle, what am I calling it up there? Just theta squared. Oh, sorry, just theta. Right? So its typical lateral speed will be v0 times the typical theta, or the root mean squared value of theta. Right? So the distance this blob will have moved in this time t grows like time times that typical velocity. So it goes like time times the root mean squared value of theta. Okay? Now, we calculated the root mean squared value of theta back when I was deriving the Mermin-Wagner theorem. And what we found was that root mean squared value of theta goes like r to the 1 minus d over 2. So if I jack that result into here, and I say that the radius is growing like the square root of time, I can say how this delta x perp, how much this blob will have moved laterally, how far this blob will have moved laterally in this time t. And if I do that, I find it's moved laterally a distance that goes like time to a power. And the power depends on the dimension of space. And that power is 1/2 minus d over 2. Okay? Follow that? So I would plug that in for theta, the root mean squared value of theta, into this expression and ask, what's delta x perp? How far has the blob actually moved from side to side? It's literally just a matter of counting on your fingers. You find delta x perp goes like t to a power, and that power is 3/2 minus d over 4. Okay. Well, so what? Well, how does that compare with the size of this blob? Well, the size of this blob, we know, grows like the square root of time. So the distance it's moved laterally divided by its width grows like this divided by t to the 1/2. And that ratio, counting on your fingers, goes like t to the power 1 minus d over 4. And now you see again, there's a critical dimension. But it's different than the one we got the last time. If d is greater than 4, if you had a 5-dimensional flock, which of course you'd never have in reality, but you could simulate, this ratio goes to 0 as time goes to infinity. So what that means is any fluctuating region that's correlated has moved very little distance compared to the size of that region. So effectively, you're going to be insensitive to the fact that you're moving, and you're going to behave like a system of pointers. But if d is less than 4, this power is positive, and as time gets bigger and bigger, any correlated blob is going to have moved from side to side a much bigger distance than the size of the blob itself. So what that means is, if I'm a bird over here, and I'm waiting to find out what's going on with this bird over here, I don't have to wait for this blob to grow diffusively until it reaches me. All I have to do is wait for this blob to wander from side to side far enough that it bumps into me. In other words, information in this flock is not being transmitted diffusively, by word of mouth from one bird to its neighbor to its neighbor. It's being transmitted convectively by the fluctuating regions moving laterally through the flock and carrying the information that way. That's why it was only the diffusion constant in the perpendicular direction that diverged in the hydrodynamic calculation that you, Hai-Tu, and I did. Okay, any questions about that? It's an involved argument, but it really is just counting on your fingers. Erwin first and then you.
How would you modify that argument to see the phase transition?
Can I think about that and answer it tomorrow? The short answer right now is I don't know. I've never tried to do this kind of argument for the phase transition, but you're right, it ought to be possible to do that, but I can't see it off the top of my head. Yeah. I'm sorry, it depends on. No, V0 is a constant here. It just depends on the direction fluctuating. In fact, I assumed in this calculation that V0 was a constant. Sorry. The argument doesn't actually depend on. Oh, sorry. Okay, yeah. Of course, the speed actually fluctuates, right? So there is actually motion of this blob up and down, but that motion doesn't grow with time, or rather, it only grows diffusively, right? If I'm walking in this direction and my speed is statistically fluctuating in a way that has no long-range correlations in time, then if you ask for the probability distribution of my position, it'll be centered at my mean speed times time, and its width will grow diffusively. Okay, so I misspoke. This blob will actually get an enhancement in its spread along the direction of motion due to fluctuations in the speed, but that enhancement is just a finite addition to the diffusion constant. The lateral motion is giving an addition to the diffusion constant, which grows unboundedly with time. That's the difference. And you can see that because this is growing, you know, it's not that delta x perp is going like W, it's going faster than W. Okay.
One thing about the motion of the entire domains.
Mm-hmm.
So basically, domains that move with different velocities can go through each other. If birds have an excluded volume, would that change?
Yeah. Really, you're catching. There's something in this argument that I'm sweeping under the rug, which is that the motion in the flock is actually not diffusive. There's actually propagating sound waves, because if you have something coming in from this side this way, something coming in from this side this way, they compress the material in the middle, and that pressure force I wrote down pushes them back out. Okay, but it turns out you can dress this argument up and take that into account. The important thing is, what's the dissipative mechanism? The dissipative mechanism is diffusive, and so this argument still works. But you're actually right. The picture isn't really that you have domains that are passing through each other. It's really sound waves and how they decay, but that makes the picture a little more complicated, but doesn't actually change the result. Okay, so the conclusion you come to from this argument is that in d less than 4 the physics changes, and what changes is the linearized hydrodynamic theory breaks down. Okay, that's the breakdown of linearized hydrodynamics that I talked about. So what really happens in d less than 4? What really happens is that a blob defined as a region that's affected by what was going on at the origin at time t equals 0 grows anisotropically. The width in this direction grows like the square root of time. Part of the coefficient of that square root of time is the diffusion constants, the passage of information by word of mouth. Part of it is fluctuations in the speed, and that certainly contributes to it, but it still grows like the square root of time. But the lateral dimension of the flock grows like some w perp of t, which remains to be determined. And now I'm going to determine that just by going through the same argument that I went through when I was deriving the Mermin-Wagner theorem, but taking into account the fact that this width is growing due to this convective mechanism. Okay? So we have this blob. The number of errors per spin still goes like time. The number of spins now goes like the area. I'm doing now specifically 2 dimensions. Goes like the area of this region, which goes like its width in the perpendicular direction times its width in the parallel direction, which is the square root of time. So the number of errors goes like that area times time. So it goes like the width times time to the 3 halves. So the root mean squared error goes like the square root of that. The root mean error, squared error per spin goes like the square root of that divided by the number of spins. So it goes like that over that. If you do the arithmetic of working this out, you find this goes like t to the 1/4 divided by w perp to the 1/2. Okay? And now what you say is we have an estimate of w perp. W perp goes like v naught fluctuation in the angle times time. Here's the fluctuation in the angle, so we get an equation for W perp, which involves time and involves W perp. Well, that's a self-consistent equation. We can solve that. It's just algebra. And what you find is that W perp grows like t not to the 1/2 power, which is what we got when we were doing the diffusive law, but like t to the power 5/6. And the crucial thing about that is 5/6 is bigger than 1/2, so in the limit of t going to infinity, t to the 5/6 is much bigger than t to the 1/2. That ratio goes to infinity, and that's the sense in which the diffusion constant is infinitely enhanced in the long time limit. And now if you take this result for W perp and plug it into here, the expression for the root mean squared fluctuation in the angle, you'll find that the root mean squared fluctuation in the angle decays with time, like t to the minus 1/6, so it goes to 0, so we've gotten around the Mermin-Wagner theorem. And that's where long-range order comes from in a flock. So basically what happens is the very effect that you would think would disorder the flock is enhancing, that is, the wandering in the direction of motion, is enhancing the transport of information perpendicular to the mean direction of flock motion so much that it's suppressing, stopping those fluctuations from getting so big that they can actually destroy the order. Okay. This is starting to give me an idea of how I might answer Irwin's question, so I'm think along these lines a bit more. But that's the mechanism by which you get long-range order. And it's pretty amazing. It's fundamentally nonlinear because the physics of this lateral transport is basically coming from that convective term, which is a nonlinear term. So it's quite an amazing problem. It's quite an amazing result. And it's one of the first things we understood in active matter, which is really quite nice. OK, so one last bit of the story. There's an object lesson in this for all graduate students and all advisors of graduate students in the audience. When I started at University of Oregon, I had a student named Marcus Ulm came by and asked if I could give him a project to work on. First, I wanted to give him something pretty simple, and I figured for somebody of his generation, a simple thing would be a computer simulation. So I suggested that he simulate the Vicsek model with these sorts of boundary conditions. So the boundary conditions here are reflecting walls on the left and the right, periodic boundary conditions on the top and the bottom. So what will happen in this system is that if you're in the ordered state, the flock can only choose to move either straight up or straight down. Okay. Now, a lot of people at this point say, well, wait a minute, you've broken rotational invariance when you've done that. I haven't, because I'm using the same Vicsek algorithm that I used before. Rotation invariance is only broken on the boundary. The only way someone in the middle can find out about that is if I develop long-range order. Okay? If I don't develop long-range order, then they'll never know about those boundary conditions, and the situation will still be rotation invariant. So I still have to break a continuous symmetry to get order here, but if I do, I know the velocity has to be either straight up or straight down. So I gave Marcus this problem, and he disappeared for 3 months. And I thought he just lost interest or given up or something. And then he came back and very sheepishly said, you know, I did that simulation you told me to do, but I just couldn't get it to work. No matter how many times I did it, I kept getting this weird situation in which the fluctuations were very well correlated perpendicular to the direction of motion, but not very well correlated parallel to the direction of motion. And something clearly is wrong with the code. And I scratched my chin for a minute, and then I realized, wait a minute, good correlations perpendicular to the direction of motion, worse parallel to the direction of motion. That's what the theory predicts. So this looks, even to the naked eye, very different from a simple fluid, and it's because of the nonlinear hydrodynamics, because of this nonlinear spreading mechanism that I was talking about. And in fact, when we analyzed the correlations in this simulation, we found they were exactly what's predicted by the hydrodynamic theory. So the two morals are, if you're a graduate student, you're getting something weird, don't hide from your advisor, talk to him about it. You may have made a discovery. The other piece of advice is, if you're an advisor and your graduate student disappears, track him down because you might be onto something. Okay. And if he tells you something you don't believe, listen to him and think about it, or listen to her and think about it. Okay. All right. So with that moral lesson in hand, one other thing. Okay. I'll tell you the rest of the story tomorrow. Thanks for your patience and hanging around. Excuse me, just before I